Welcome everyone to part F of lecture 2. We're going to be talking about balancing reactions and stoichiometry. And if you've had chemistry before, which I assume most of you have, you know that balancing reactions is one of the core functions that we do in chemistry before we can do anything, any kind of predictions about how much stuff we need to put in, how much stuff we expect to get out of a reaction. We need to have a balanced reaction, and we need to understand how those ratios work, and that's called stoichiometry. So first, let's look at balancing reactions and why we do it. Let's take a look at a very simple reaction between H2 and I2, just two diatomic molecules that are going to smash into each other here. So first thing we want to do is we want to shrink ourselves down to molecular size. So we're going to pop down really small, and we are going to hop into our little molecular sized jet, and we're going to fly around this gas phase reaction where I have H2 gas molecules and I2 gas molecules. So when we're down to a molecular size, what would we see while we're there? Well, we're going to see a chemical reaction actually taking place. And when that reaction takes place, what we're going to see is our hydrogen molecules and our iodine molecules slamming into each other. We see we've got a release of energy there. And what comes away from that, we break our iodine-iodine bond from that collision, we break our hydrogen-hydrogen bond from that collision, and we form a couple of new bonds. So now we have two hydrogen iodide bonds being formed, and that gives us two hydrogen iodide molecules as a result. So the question we want to ask ourselves is this reaction balanced as we have it written, and has mass been conserved? Well, if we take a look at what we have in that picture between H2 and I2, we've got two hydrogen atoms here in the H2. We've got two iodine atoms here in the H2. We see those two species colliding right there. And then we still have two hydrogen atoms. They're separated, but we still have two hydrogen atoms, and we still have two iodine atoms. And so we have, in fact, conserved mass, and that means that our reaction is in fact balanced in our picture. But as you can imagine, trying to draw a picture every time that we want to do a chemical reaction might be a little bit complex, especially when we have larger molecules. So what we want is we want a way to write our chemical reactions in a very simple shorthand way. And so to do that, we just write the chemical formula. So here we would say H2, that's an H2 molecule. The two after that H there indicates that we have two hydrogen atoms. I2, that's an iodine molecule, indicates we have two iodine atoms. And then we have two HI molecules. Notice that the formula of HI is just HI, and I have two molecules of HI, so I put that 2 out in front of the HI. I don't write H2I2 because that would indicate that I have a molecule with two hydrogen atoms and two iodine atoms, and that is not what I have. I have two HI molecules, so that's why we write it that way. And so we can see, in fact, that when we write it that way, we have balanced our reaction and we have conserved mass. Let's take a look at an unbalanced example and see how we might balance this. So the reaction of hydrogen gas and oxygen gas is one that gives us water, H2O. We always want to check a reaction to see if it's balanced. We see there on the left that we've got two hydrogen atoms and two oxygen atoms there. Okay, good. Over on the right, we have two hydrogen atoms. That's looking good. Oh, we only have one oxygen atom though, and so things are not balanced. Okay, so now we have to balance our reaction. Okay, we see there it's not balanced. It looks like a little smile. It's not actually a smile that it's not balanced. It's just indicating that those two numbers are not equal, so my reaction cannot be balanced. Now, one thing I've seen done before that you cannot do is to change the formula of the reaction, or to change the formula of a product or a reactant. So it would be very easy just to add a little 2 there after that oxygen and water to give us H2O2 and say, oh, it's balanced. That's true, it would be balanced, but now rather than making water, the reaction would be making hydrogen peroxide, and that's a different chemical. And so all of a sudden we've changed our reaction, and we're not allowed to do that. So we can't change the formulas of our reactants or our products, but what we need to do is to adjust how many of each species we have in order to balance the reaction. So let's see how we would do that. So there's our reaction. H2O2 goes to H2O. We need two oxygen atoms on the right because we have two on the left. So if I had two water molecules, that would give me 2 oxygen atoms in the products there. So let's see what that does. So now we have H2 plus O2 goes to 2H2O. All right, so now on the reactant side, I have 2 hydrogen atoms from the H2. I have 2 oxygen atoms from the oxygen, so that hasn't changed. That's good. But now we have 2 water molecules, and so while I have balanced my oxygen atoms at 2, I've now thrown my hydrogen atoms out of balance because now I have 4. So it's still not balanced. That doesn't mean that what we did was wrong. It just means that we're not balanced yet. Is there something else that we can do in order to get 4 hydrogen atoms over in the reactant side? And there is. Okay, I can balance those hydrogen atoms by having 2 H2 molecules. That will leave the oxygens alone. They're already balanced. And it will bring up the number of hydrogen atoms in the reactants to 4. And so now if we look, I have 2 H2, that gives me 4 hydrogen atoms. O2, that gives me 2 oxygen atoms. And then over with the 2 H2O, that gives me 2 water molecules, which gives me a total of 4 hydrogen atoms and 2 oxygen atoms, just like we have in the reactant side. So we are, in fact, balanced there. Now, when we balance a reaction like that, where we're just looking at the different numbers and changing, it's really kind of a trial and error approach, and we call that balance by inspection. So all we do is we try something and we check it, and we try something else and we check it, and we keep going until we're balanced. So here's an example for you to try on your own. I do have a solution to this posted in YouTube, and so you can see there'll be a link to it, and you can check out how to do that one. And here's another one for you to try. A little more, I don't know if it's more difficult or not, but you'll have some different coefficients, obviously. So I will post the link with this one as well. Actually, the one before it and this one will probably be in the same video. All right, so here's a term that sometimes scares some people in chemistry because it's a really weird sounding word if you haven't been exposed to it before. And this is something called stoichiometry. It's basically a Greek rooted word that means how much, okay, in essence. So what we're doing in chemistry is relating moles of one substance to moles of another. It doesn't have to be reactant to product. It can be reactant to reactant, product to product, whatever. It's just relating how much of one thing to how much of another. A completely non-chemical way of looking at stoichiometry is to look at the numbers involved in a recipe, okay, where you have grams or kilograms or liters and milliliters. By knowing how much of a recipe we put into, how many ingredients we put into a recipe, we can figure out how much we are going to get out. For example, if you were making, I don't know, something at home and it called for 250 grams of ground beef, of hamburger, and you say, well, that's not going to be enough. I need to use half a kilo. I need to use 500 grams. How much can I find a recipe that uses that much? Well, we don't have to find a new recipe. We just have to double everything, right? That's stoichiometry. That's all that is. Okay, so here's an example of making cheesecake. Pay no attention to the H2N2 NH3. That does not belong in cheesecake. That'd be the nastiest cheesecake ever. So imagine that we had 5 eggs, 3 blocks of cream cheese, and 1 cup of sugar. That would make the filling for 1 cheesecake. Okay, what if I wanted to make 2 cheesecakes? Do I need to find a new recipe? No, I just need to double everything. So if I wanted to make 2 cheesecakes, I have these ratios, I have these relationships between the number of eggs, the blocks of cream cheese, and the cup of sugar to get 1 cheesecake. Okay, so if I wanted 2 cheesecakes, I would need 10 eggs. If I wanted 2 cheesecakes, I would need 6 blocks of cream cheese and 2 cups of sugar. That is all stoichiometry. That's all stoichiometry is. It's just looking at those relationships between reactants and products. Let's look at an actual chemical reaction here. Now we'll look at the ammonia. 3H2 plus N2 goes to 2NH3. There's lots of different conversion factors here that go from moles of one thing to moles of another. So let's say we have 5 moles of N2. We want to know how much NH3 can we make, assuming we have all the H2 that we need. Okay, well, we see that we have a lot of different mole-to-mole conversions here. We have 1 mole of N2 per 2 moles of NH3, or 1 mole of N2 per 3 moles of H2 or 3 moles of H2 per 2 moles of NH3. Okay, we're looking for a conversion factor between moles of N2 and moles of NH3. And we see that we need 1 mole of N2 for every 2 moles of NH3. And you might wonder where those numbers came from. Well, they came from the balanced reaction. So remember, this is a 1 here in front here. So I have 1 mole of N2 for every 2 moles of NH3. I have 1 mole of N2 for every 3 moles of H2, or changing the color again, 3 moles of H2 for every 2 moles of NH3. Okay, that's all that's doing is setting up all of those conversion factors. Okay, so to answer our question, if we have 5 moles of N2, how much NH3 can we make? Well, we know that we get 2 moles of NH3 for every mole of N2. So if I have 5 moles of N2, I can make 10 moles of NH3 because 5 times 2 would equal 10. Okay, so I actually have 6 different mole conversion factors here because I have the ones that I have written here. The other thing I can do is I can invert every one of those and get the inverse relationship between the number of moles. Now, a lot of times when we're doing a reaction, we don't often add our reactants in exact amounts. So in that sense, chemistry is not quite like cooking. Okay, because when you cook everything that you add in, you're going to be eating. It's going to go into all the food. It's not quite that way with chemical reactions, because once something runs out in a chemical reaction, the reaction stops. It doesn't keep reacting with what's still left because it can't. So with chemical reactions, there's often one present in excess. In other words, there's more of that chemical than you need. And what that means is that there's less of one than you need to react with the one that's in excess. And one of those will run out first. And it's the one that doesn't have enough material to react with the larger one. So that reactant that runs out first is called the limiting reactant. And we call it the limiting reactant because it limits how much product you're going to get out. It controls the amount of product produced by the reaction. So there we go. So let's go back to our NH3 reaction and take a look at how we might do this. So let's say that we have 10 grams of H2 and 10 grams of N2. Now we might say, oh, well, we have the exact same amount of H2 and N2 because we have the exact same mass. But remember that chemical reactions do not happen in terms of mass. They happen in terms of number of molecules or number of moles, because molecules react. Grams don't react. So the number of molecules can be directly related to the number of moles. So we need to look at the number of moles of each of those reactants that are present. Okay, in doing that, we can figure out how much NH3 will be produced. Now, when we look at this, we can't just assume we're going to get 20 grams. We can't assume that all of the H2 and all of the N2 will be used. Okay, whenever we have amounts of 2 different reactants, we generally have to assume is that one of those is going to run out first. That's not always the case, but it's always good to check. Okay, so let's see if we have a limiting reactant problem. So let's work this one out. First thing we want to do is we want to convert both reactants to moles. Okay, because remember, everything happens in terms of moles. So 10 grams of H2, we use our conversion factor there between moles and grams to get moles of H2. Notice that we've got 2 grams per 1 mole for H2 because I have 2 hydrogen atoms in a molecule of H2. It's really easy to just say, oh, I have hydrogen, look up at the periodic table, see hydrogen at 1.007, and say that's my molar mass. Okay, but that's for an atom of hydrogen or a mole of hydrogen atoms, not a mole of hydrogen molecules. So got to make sure you get that molar mass right. So we end up having almost 5 moles of H2. Now 10 grams of N2 doesn't give us nearly the same amount of moles because N2 is a much larger molecule. Nitrogen is a much larger atom than hydrogen, and so it weighs more per atom, and so the molecules weigh a lot more as well. So we don't have nearly the same amount of N2. So now we need to see which one of these is going to run out first. Okay, now we can't just look at the number of moles and assume that the species with the fewest number of moles will run out first, because if they have different balancing coefficients, that tells us that they are used at different rates. Okay, it's kind of like if you were building a car, we know that tires get used up at a rate 4 times faster than steering wheels, because I only need 1 steering wheel per car, but I need 4 tires per car. So if I had 3 steering wheels and 10 tires, the tires are going to run out first, because I can only make 2 cars with 10 tires, but I could make 3 cars with 3 steering wheels. And so my tires are going to run out first, even though there's more of them, and that's because we use them more per car. Okay, same idea here with our stoichiometry. So there's lots of different ways of doing this. This is the way that I always teach it. If you learned and remember a different way to do it, it's probably correct, and you're welcome to use your way as well, as long as it produces correct, consistent results. Okay, so we take the number of moles that we found in step 1, we divide it by the coefficient that we have in the balanced reaction. Since the coefficient of nitrogen is a 1, then we divide that by 1. Obviously, we end up with the same number, 0.3571. For the hydrogen gets used up 3 times faster. So we had 4.975 divided by 3 from the 3 coefficient, and I get a value of 1.658. Now, since this number is less, this is my limiting reactant, and that means that the moles of nitrogen are what I want to use in order to calculate how much product I'm going to get. I no longer need to worry about how much hydrogen I have. Okay, so we know that the nitrogen will be the limiting reactant. We're going to use its moles to determine how much product is formed. And so I go back to my moles of N2, 0.3571. I know that I get 2 moles of NH3 per mole of N2. That's again based on the stoichiometry in the balanced reaction. And so I end up with 0.7142 moles of NH3. And I can then take that to grams using the molar mass of ammonia, which we calculated in the previous lecture part at 17 grams per mole. And so I have 0.7142 moles of NH3. Notice that all my units are going to work out here. So my moles of N2 cancel, leaves me with moles of NH3. Here my moles of NH3 cancel, and I'm left with grams of NH3. Unit analysis is a very powerful tool. Be sure you're using it in these types of calculations. So what we find is if we put in 10 grams of H2, 10 grams of N2 into a reaction, I'm going to expect that I get 12.1 grams of NH3 out of that reaction. Now, in a perfect world, that's how much product we would get. We'd put in 10 grams of H2, 10 grams of N2, and we should get 12.1 grams of NH3. However, this very rarely occurs, that we get a perfect reaction occurring. Lots of different things can happen. Perfect example is something like cookie dough. If you've ever bought the little tubes of cookie dough, or if you made your own cookie dough, you look at the recipe or you look at the package and it says makes 24 cookies, 24 cookies. We never get 24 cookies out of that, because lots of different things can happen. You can make the cookies too big because you like big cookies. Well, if you make the cookies too big, you're not going to get as many cookies out. So you've now limited the yield of your cookies. Or more likely what happens is you walk past and say, "Ooh, boy, that's some good looking cookie dough." And you take a little piece and you eat it. Your little brother comes by and says, "Ooh, cookie dough." And he comes by and eats it. Your dad, your mom comes by and says, "Oh, I love cookie dough." And in it goes. And all of a sudden, you don't have as much cookie dough as you expected, and you don't get as many cookies as you wanted. Okay, now we don't have people walking past and eating our chemicals, so that's not really what happens. We do get things like side reactions or other kinds of reactions, or we can set up an equilibrium inside the reaction that we'll talk about later in the course. But that an equilibrium situation can start destroying products and recreate some of your reactants, and the amount of your product created gets limited a little bit. So lots of different things can happen. Let's look at that last problem that we did. We saw that for 10 grams of N2 and H2, we should get 12.1 grams of NH3. Okay, what we expect to get out is called the theoretical yield. This would be like the 2 dozen cookies that we get or that we expect to get out of our cookie dough. Theoretical yield, what you should get theoretically. So let's say that we do our reaction with 10 grams of N2, 10 grams of H2, we recover our product and we find we only have 7.8 grams of NH3 that we recover. Well, what happened? Again, lots of different things can happen here. It's not really important what happened, but at this point you want to know what is your percent yield, what is your actual yield. So the 12.1 grams is your theoretical yield, what you expected to get out. 7.8 grams is the actual yield. This is what really happened when you did the reaction. Okay, an important thing with actual yield is it is a measured value. It can't be calculated, and yes, unless you have the percent yield as well. But you cannot look at a reaction and say, oh, well, I'm going to get that much out of a reaction. Generally, you have to do the reaction and measure out how much product was produced. So to calculate percent yield, we're just going to look at the ratio of actual yield to theoretical yield. So we take actual yield, divide by theoretical yield, we multiply it by 100%, and that gives us our percent yield. So for this problem, we have 7.8 grams divided by 12.1 grams times 100%, and we get 64.4%. Percent yields can go all over the board. Some really well-behaved reactions can have percent yields up in the 90s. Other reactions that are really complex, that have a lot of different reaction paths for side reactions, you may yield only between 5 and 10%. It just depends on the type of reaction and what's going on, the conditions, and how well it's controlled. So here's one for you to try. We've got a reaction that uses aluminum sulfide and water. We want you to balance the reaction. Notice that we've got the lines in front there. So balance that reaction, determine the limiting reactant, and calculate the mass of H2S that you would expect to form. So calculate that theoretical yield of H2S. And the solution for this one will also be posted on YouTube. And if you have any questions on this particular lecture, make sure you contact me.